Well, now we've completed our discussion of what to do when the number 4 priority is pointing away from you into the page. We've discussed the mechanical method that allows you to determine whether the stereocenter is R or S if the number 4 priority is pointing away from you. But remember, there's really two different cases we need to deal with. We have to learn what to do when the number 4 priority is pointing into the page, and case 2, we have to learn what to do when the number 4 priority is not pointing into the page. Well, now we're done with case 1. We know what to do when the number 4 priority is pointing away from you into the page. Now, as we proceed with the videos, we have to move on to case 2. What do you do when the number 4 priority is not pointing away from you? It's going to help to look over a trick. This trick is called the single swap rule. What happens if you make a single swap around a stereocenter? If you make a single swap around a stereocenter, that will always give you the opposite configuration. This is a really useful trick, so let me give you some examples to show what I mean by that. This is an example that we already did. We already figured out that this molecule has the R. This stereocenter has an R configuration. Now, what would happen if we made a single swap? What would happen if, say, we swapped the iodine and the bromine? Here's what I mean by that. We're going to keep the chlorine and the fluorine in the same positions as before, but where the iodine used to be, I'm going to write the bromine. And where the bromine used to be, I'm going to write the iodine. And the only reason I'm putting these dots in here is to draw your attention to the fact that these are the two atoms that we're swapping. So you can see that this is what I mean by saying making a single swap. It means taking the original picture and redrawing it exactly, except that you swap the positions of two of the groups. Now, what's going to be the configuration of this molecule? Well, we should not have to go back to first principles and figure this out from scratch because we just learned the single swap rule. The single swap rule is that anytime you make a single swap, that always gives you the opposite configuration. Since we already knew that this had an R configuration, we know automatically that after the single swap, we're going to have an S configuration. So go ahead and be my guest and check that this is really an S configuration. The number 4 is still pointing away from you, so it shouldn't be too hard to use the method we've already learned to confirm that this is S. But the good news is that you don't have to do that. Since we know that we got to this picture by making a single swap in this picture, we know it must have the opposite configuration. Let me give you another example of the single swap rule. Let's start again with this same molecule. We already know this molecule has an R configuration. This is one of the examples we previously did. But now let's swap the chlorine and the bromine. So the chlorine is going to move from left to right, and the bromine is going to move from right to left. And again, I'm just using the dots to indicate that those are the atoms that I swapped. Now, if this picture is an R, and I made a single swap, what's the configuration of this picture? It must be an S. That's the way the single swap rule works. Again, you can use the method we've already learned to confirm that this is S, but you shouldn't. We don't really have to do that now that we know the single swap rule. If you make a single swap, that always gives you the opposite configuration. By the way, now you can see that I really mean any single swap. So in the original example that I gave you, I swapped the iodine and the bromine, which were kind of next to each other in the picture. And now in this new example, I swapped the chlorine and the bromine, which are kind of opposite each other in the picture. But it doesn't matter what the original relationship is of the two groups, any single swap will always give you the opposite configuration. The single swap rule is a really useful trick when you're working with stereochemistry, not just for R and S naming. There's other aspects of organic chemistry where it's useful as well. But obviously in this video we'll be mainly focusing on how we can use the single swap rule to find a mechanical process for doing R and S naming. This is another example that we already did previously, and we already saw previously that this has an R configuration. So what's the configuration of this molecule? Well, it should be immediately obvious that we've made a single swap, so this is an S. What did we swap? Well, we swapped the fluorine and the hydrogen. In this picture, the fluorine is on a wedge and the hidden hydrogen is on a dash. And in this picture, the fluorine is on the dash, so the hidden hydrogen is on the wedge. Since we made a single swap, that should change the configuration from R to S. So the single swap rule works not just for Fisher projections, but also for non-Fisher projections. Now, maybe it's not quite as obvious, but this picture also differs from this picture by a single swap. Now, in this case, I've swapped the fluorine and the methyl group. If you compare the dots, you can see that we've swapped the fluorine and the methyl group. The fluorine went from the wedge to in the plane of the page, and the methyl group went from the plane of the page to a wedge. So, what is the configuration of this stereocenter? Well, we know automatically, since we made a single swap, since this picture is R, this picture must be S. So once again, this confirms that the single swap rule works for any single swap. A couple of seconds ago, I talked about swapping the wedge and the dash. We swapped the fluorine and the hydrogen from one was on a wedge and one was on the dash, and we swapped their positions. But you don't have to swap the things that are on the wedges and the dash. You can also swap with the things that are in the plane of the page. Any single swap will give you the opposite configuration.